Hello, my dear students. In this video, we are going to discuss about periodic motion and non-periodic motion, then simple harmonic motion from the chapter Oscillation. Chapter name Oscillation, and the topics are periodic and non-periodic motion, then simple harmonic motion. Right. Right. In the previous chapters, that is in kinematics and laws of motion, we have to discuss about translatory motion and rotational motion. Translatory motion and rotational motion. Right. What is meant by translatory motion? If the motion of the particle is along the straight line path, then it is called translatory motion. For example, a man walking on a straight road, or a car is moving along a straight track, or an insect moving on a wall. So these are a few examples of translatory motion, right? The motion of the particle along the straight line path is known as translatory motion, right? And what is meant by rotational motion? If the motion of the particle along the circular path, then it is called rotational motion. The rotational motion is also called circular motion. Circular motion. Example, the rotation of electron or a revolution of electron around the nucleus. The revolution of electron around the nucleus, or the revolution of planets around the sun. The revolution of planets around the sun. So these are a few examples of rotational motion, right? So translatory motion and rotational motion are discussed in the previous chapters, that is in kinematics and laws of motion. Am I right? Right. In this session, we are going to discuss about periodic motion and non-periodic motion, then simple harmonic motion, right? And another important type of motion is also there, that is oscillatory motion. Oscillatory motion. Oscillatory motion. Oscillatory motion is also called vibratory motion. Oscillatory motion is also called vibratory motion, right? What is meant by oscillatory motion? Okay, simple definition for oscillatory motion is the to and fro motion is called oscillatory motion. The to and fro motion is called oscillatory motion, or otherwise defined as if the particle moves front and back or forth and back repeatedly at a fixed interval of time. Okay, if the particle moves back and forth repeatedly after regular interval of time or a fixed interval of time is known as vibratory motion or oscillatory motion. Once again I repeat, to and fro motion is called oscillatory motion, or otherwise defined as if the particle moves back and forth repeatedly after regular interval of time. After regular interval of time is known as oscillatory motion, or it is also called vibratory motion. Right? Example, the oscillation of a simple pendulum. The oscillation of a simple pendulum. Next, Anson pendulum clock. Anson pendulum clock. Right? Next, heartbeat. Heartbeat is one of the best example for oscillatory motion or vibratory motion. Vibratory motion. So the oscillation of a simple pendulum, Anson pendulum clock, and heartbeat. So these are a few examples of oscillatory motion or vibratory motion. Right. The oscillatory motions are periodic motion. The oscillatory motions are periodic motion. Why? Because in this motion, the particle moves repeatedly after regular interval of time. Okay, in oscillatory motion, the particle moves repeatedly after regular interval of time. So that is why the oscillatory motion is one of the periodic motion. Periodic motion. all the oscillatory motions are periodic motion, but all the periodic motions are not oscillatory. Understand? All the periodic motions are, all the oscillatory motions are periodic, but all the periodic motions are not oscillatory motion, right? So one of the best example for periodic motion is oscillatory motion. Okay, what is meant by periodic motion? The motion which repeats itself after a regular interval of time is known as a periodic motion. Okay, the motion which repeats itself after a regular interval of time is known as a periodic motion. Okay, examples for periodic motion: the revolution of planets around the sun. The revolution of planets around the sun. First example. Second, the revolution of moon around the earth. The revolution of moon around the earth. Third, waxing and waning of moon. Waxing and waning of moon. Okay, waxing and waning means valarprai, theiprai. In Tamil, valarprai and theiprai. So waxing and waning of a moon is one of the best example for periodic motion. Periodic motion. And next, the swing of a cradle. The swing of a cradle. Okay, so these are a few examples of periodic motion. So what is meant by periodic motion? The motion which repeats itself after a regular interval of time is known as periodic motion, right? And what is meant by non-periodic motion? The motion which does not repeat itself after a regular interval of time is known as non-periodic motion. Non-periodic motion. Example, the motion of clouds. Motion of clouds. And the occurrence of earthquake. Occurrence of earthquake. And eruption of volcano. The eruption of volcano, occurrence of earthquake, and the motion of clouds. So these are some examples of non-periodic motion. Or you understand what is the difference between a periodic motion and a non-periodic motion? The motion which repeats itself after a regular interval of time is known as a periodic motion. The motion which does not repeat itself after a regular interval of time, then it is called non-periodic motion. Non-periodic motion, right? So one of the best example for periodic motion is oscillatory motion. All the oscillatory motions are periodic, but all the periodics are not oscillatory motion. Not oscillatory motion. Understand? Right. Okay. A special type of oscillatory motion is simple harmonic motion. Simple harmonic motion. So simple harmonic motion is a special type of oscillatory motion or vibratory motion. Okay. So best example for oscillatory motion is simple harmonic motion. Okay. All the simple harmonic motions are oscillatory motion, but all the oscillatory motions need not be simple harmonic motion. Need not be simple harmonic. So all the simple harmonic motions are oscillatory motion, but all the oscillatory motions need not be simple harmonic motion. So simple harmonic motion, it is a special type of oscillatory motion. It is a special type of oscillatory motion. Right. Suppose let us consider a particle of mass m. Particle of mass m. Suppose this particle is moved from origin O to A, and then from A to O, and once again it moves downwards, that is towards B, and again from B to O. Okay, so there is a particle whose mass is m. That particle is moves between the points A and B about the fixed point O. So O is a fixed point or origin. Okay, about this point the particle moves between these 2 points. Between these 2 points, right? So particle mass is taken as m. If the particle move from the position, origin O or the point O to A, the velocity of the particle is gradually decreases and it becomes 0 at point A. Okay, so here the particle is moves in between the point A and B about the fixed point O. If the particle move from O to A, the velocity of the particle is gradually decreases and it becomes 0. Where? At point A, right? If the velocity of the particle is continuously changes during its motion, so the particle gets accelerates. The particle gets acceleration. Accelerate. The magnitude of acceleration is negative. Why? Because the velocity of the particle is decreases. If the velocity of the particle is decreases with the time, the particle has a negative acceleration. The particle has negative acceleration. So, if the particle is moved from O to A means the direction of acceleration of the particle becomes A2. That is towards the point O. Towards the point O. Right? Understand? The particle move from O to A. The velocity of the particle at every instant changes and every instant decreases. Okay, so due to the decreasing of velocity with respect to time, the particle has or the particle experience negative acceleration. Negative acceleration. The negative acceleration direction is always opposite to the direction of motion of the particle. Opposite to the direction of motion of the particle. Here, the motion of the particle is from the direction of motion of the particle is from O to A. The negative acceleration direction is from A2. A2, that is the acceleration of the particle is towards the point O. Towards the point O, right. Suppose the particle move from again A to O, the velocity of the particle is gradually increases and it becomes maximum. And it becomes maximum where? At the point O. Okay. So if the particle moves between the 2 points A and B about a fixed point, the position where the velocity of the particle is a maximum is called mean position or equilibrium position. Mean position, the mean position is also called equilibrium. Equilibrium position. Okay, the position where the velocity of the particle is a maximum is called mean position or equilibrium position. If the particle move from the point A to O, the velocity of the particle is gradually increases and it becomes maximum at point O. That point is called or that position is called the mean position or equilibrium position, right? So there is the increasing velocity of the particle. So the particle experience positive acceleration. The positive acceleration direction is always along the direction of motion of the particle. Along the direction of motion of the particle. So now also the acceleration direction is towards the point O. Towards the point O. So if the particle either move from O to A or A to O, the direction of acceleration of the particle is always towards O. Towards O, right? On other side, the particle move from O to B. Again, the velocity of the particle is gradually decreases and it becomes 0 at point B. At point B. So the position where the velocity of the particle is 0 is called the extreme position. Extreme position. Right? B also extreme position. Extreme position. The point O is mean position or equilibrium position, whereas the point A and B are extreme position. Okay? The position where the velocity of the particle is 0 is called extreme position. The position where the velocity of the particle is maximum is called equilibrium position or mean position. So in this diagram, A and B are extreme position, whereas O is equilibrium position or mean position. Right. If the particle move from the equilibrium position O to the extreme position B, the velocity of the particle is gradually decreases and it becomes 0. Right? So the particle experience negative acceleration. The direction of motion of the particle is along OB, whereas the acceleration of the particle is along BO. That is towards the point O. Towards the point O. Right? If the particle move from B to O, the velocity of the particle is increases and it becomes maximum at point O. Okay? So the particle experience positive acceleration. The positive acceleration direction is along the direction of motion of the particle. Okay? So if the particle move from O to A or move from O to B or from A to O or B to O, the direction of acceleration of the particle is always directed towards the mean position or equilibrium position. So this type of motion is called simple harmonic motion. Simple harmonic motion. Right. And suppose if any particle execute a simple harmonic motion, the acceleration experienced by the particle is always directly proportional to the displacement of the particle. Suppose let us assume it is a one-dimensional case or one-dimensional motion. For one-dimensional case, the acceleration experienced by the particle is taken as a suffix x and the displacement of the particle is taken as x. Right? If any particle executes a simple harmonic motion, the acceleration experienced by the particle is always directly proportional to the displacement of the particle from the mean position. The displacement of the particle from mean position. Right? That means if the displacement of the particle from the mean position is increases, the acceleration of the particle also increases. If the displacement of the particle from the mean position is decreases and acceleration value also decreases, right? So in simple harmonic motion, the acceleration experienced by the particle which executes a simple harmonic motion is directly proportional to the displacement of the particle from the mean position. Displacement of the particle from mean position. So A suffix S is proportional to X, or A suffix X is equal to minus B into X. Minus B into X. Right here B is a constant, okay, which measures the acceleration per unit displacement. Acceleration per unit displacement. Okay, here negative sign in this equation indicates the acceleration and the displacement are in opposite direction. Okay, so the negative sign in this equation indicates the acceleration experienced by the particle and the displacement of the particle are in opposite direction. If the displacement of the particle is along this direction, means the acceleration of the particle becomes opposite. If the displacement is in this direction, then acceleration direction becomes opposite. So the negative sign in this equation indicates acceleration and the displacement are in opposite direction, and B is a constant which measures acceleration experienced by the particle per unit displacement, or acceleration per unit displacement. Acceleration per unit displacement. We know that the unit of acceleration is meter second power minus 2 and unit of displacement is meter. So meter get cancelled. So the unit of this constant B is second power minus 2. The unit of a constant B is second power minus 2 and its dimension is t power minus 2. The dimension of a proportionality constant B is t power minus 2 and the unit of proportionality constant is second power minus 2, which measures acceleration per unit displacement, right? Acceleration per unit displacement. Okay, so this condition is only applicable for in one-dimensional case. One-dimensional case, that is, if the particle is moves in a one-dimensional space, then the acceleration experienced by the particle is denoted by A suffix x and the displacement of the particle is denoted by x. So Ax is proportional to x. If the displacement of the particle increases, acceleration also increases. If you want to remove proportional, we must introduce constant. Here the constant is taken as b. And there is a negative sign in this relation which indicates the acceleration and the displacement are in opposite direction. Right. So in this equation, for our convenience, both sides are multiplied with the mass of the particle. So here what is m? Mass of the particle which executes a simple harmonic motion. For our convenience, the mass of the particle m is multiplied in both sides of the equation. Both sides of this equation. Then this equation becomes m into A suffix x is equal to minus b m into x. If same value is multiplied on both sides of the equation, that value should not be changed. So for our convenience, both sides is multiplied with the mass of the particle which executes a simple harmonic motion. So m into A suffix x is equal to minus b m into x. Right. Here according to Newton's second law of motion, F is equal to ma. Here m into Ax can be written as F suffix x. So F suffix x is equal to, here B is the constant of a proportionality, here m is a mass of the particle. for a given particle which execute a simple harmonic motion whose mass does not change. So mass value constant and B value also constant. So instead of the product of B and M, we can write or we can take K. So K into X. Here K is called force constant or spring constant. Force constant or spring constant. What is force constant or spring constant? Okay, force per unit displacement or force per unit length is known as force constant. K is equal to F suffix X. Okay, force per unit displacement is called force constant or spring constant. Right? Here, negative sign indicates the force and the displacement are in opposite direction. Force and displacement are in opposite direction. If the displacement is in upward direction, then this force direction becomes downward. If the displacement direction is downward, then force direction becomes upward. So it is indicated by negative sign. And K is called force constant or spring constant, which is defined as force per unit length or force per unit displacement. Right? Unit of force is Newton and unit of displacement is meter. So Newton meter power minus 1 is the unit of spring constant or force constant. Unit of the proportionality constant B is second power minus 2. Second power minus 2. But the unit of spring constant or force constant is Newton meter power minus 2. Okay, Newton equivalent unit kilogram meter second power minus 2 into meter inverse. Okay, instead of N, we can write kilogram meter second power minus 2. So meter inverse gets cancelled. So kilogram second power minus 2 is another unit of spring constant or force constant. So spring constant or force constant has two units. One is Newton meter inverse and another one is kilogram second power minus 2. Kilogram second power minus 2. And its dimension right, m power 1, L power 0 and T power minus 2. So this is dimensional formula for spring constant or force constant. The dimensional formula for the constant of proportionality is T power minus 2 and its unit is second power minus 2. But unit of force constant or spring constant is either Newton meter inverse or kilogram second power minus 2. Kilogram second power minus 2. Here the proportionality constant B is defined as acceleration per unit displacement. Acceleration per unit displacement. But here force constant or spring constant is defined as force per unit length. Force per unit length. Right. What is meant by force constant or spring constant? The force constant or spring constant is denoted by K, which is equal to force per unit displacement or force per unit length. Unit length means 1 meter. Unit length means 1 meter or unit displacement is 1 meter. So force per unit displacement or unit length is known as spring constant or force constant. Spring constant or force constant. Right. Okay, here the condition is Fx is equal to minus K into X. Already you know that. Here the negative sign indicates the force and the displacement are in opposite direction. So this equation also applicable for one-dimensional space. For one-dimensional case, okay, in simple harmonic motion, the force is represented by S suffix X is equal to minus K into X. Minus K into X, right? In the case of 2 or 3-dimensional space, or 3-dimensional case, this relation can be written or should be written in vector form. That is, Fx vector is equal to minus K into R vector. Fx vector is equal to minus K into R vector. For a 2-dimensional or a 3-dimensional case, in simple harmonic motion, the force can be written as f suffix x vector is equal to minus k into r vector. For one dimensional case, the force is represented by f suffix x is equal to minus k into x. Right here, the r vector may be x into I cap plus y into j cap or z into k cap for a 3-dimensional case. For 2-dimensional case, r vector is equal to x into I cap plus y into j cap. Okay, so for 2 or a 3-dimensional case, the force, in simple harmonic motion, the force is written as f suffix x vector is equal to minus k into r vector. That is, the force should be right in vector form, right? Next, one more thing. This force is called spring force. This force is called restoring force. So in this equation, the force f suffix x vector is called restoring force. Okay, why it is called the restoring force? If any particle executes simple harmonic motion, this restoring force is always tries to bring back the particle to its original position. Original position means mean position or equilibrium position. Okay, the force which tries to bring back the particle to its original position, then the force is called restoring force. In simple harmonic motion, the particle experiences a force. Okay, that force is always tries to bring back the particle to the mean position or equilibrium position. So that is why that force is called restoring force. Right? So here there is a linear relationship between this restoring force and the displacement. Okay, linear relationship means if you draw a graph between the restoring force and the displacement, the nature of the graph is always a straight line. Okay, suppose if we draw a graph by taking force along the x-axis, the restoring force is taken along the x-axis and the corresponding displacement r is taken along the y-axis. The nature of the graph is a straight line. The nature of the graph is straight line which is passing through the origin. Okay, here the straight line lies in second and fourth quadrants. Okay, so that is why I am told the restoring force and the displacement is always as a linear relationship. Why? Because if the graph is drawn between restoring force and the displacement, the nature of the graph is a straight line which is passing through the origin. That line or the straight line lies in second and fourth quadrant. Right. Suppose if we take slope for this straight line, by drawing between any 2 points on this straight line, we can measure the slope of the straight line. From the slope of the straight line, we can measure or we can calculate what is the value of the spring constant or force constant. Okay, so in the force displacement graph, the nature of the graph is a straight line. By taking a slope, from the slope we can calculate or we can measure the value of a spring constant or force constant, because the slope is equal to r divided by f suffix x. Slope means the change in value along the y-axis divided by change in value along the x-axis. That is the slope. Slope means dy divided by dx. That is change in quantity in y-axis divided by change in quantity in x-axis. Which quantity is taken along the y-axis? Displacement. And which quantity is taken along the x-axis? Force. So slope is equal to r divided by fx. So which is equal to 1 divided by k. Here k is equal to fx divided by x. So 1 divided by k is equal to x divided by f suffix x. This is for 1-dimensional case. For 2-dimensional case, 1 divided by k or 2 or 3-dimensional case, 1 divided by k is equal to r divided by f suffix x. R divided by f suffix x, right? So here R divided by f suffix x is equal to 1 divided by k. Therefore, k is equal to 1 divided by slope. So by measuring the slope for force and displacement graph, from which we can calculate what is the value of spring constant. What is the value of spring constant, right? Okay. So far we discussed about periodic motion and non-periodic motion, oscillatory motion and simple harmonic motion. Simple harmonic motion, right? Let us recall from the beginning. First, periodic motion means the motion which repeats itself after regular interval of time is known as a periodic motion. Non-periodic motion, the motion which does not repeat itself after regular interval of time is known as non-periodic motion, right? One of the periodic, best example for periodic motion is oscillatory motion. Oscillatory motion, right? What is meant by oscillatory motion? If a particle moves back and forth repeatedly at a fixed interval of time or after regular interval of time is known as oscillatory motion. The oscillatory motion is also called vibratory motion. Oscillatory motion is also called vibratory motion. A special type of oscillatory motion is a simple harmonic motion. Simple harmonic motion. What is meant by simple harmonic motion? A simple definition is there. That is, if the particle oscillates with constant amplitude and at a single frequency, then the motion is called simple harmonic motion. Okay? So simple harmonic motion is nothing but if a particle oscillates with the constant amplitude. With the constant amplitude, the particle oscillates about a mean position with the constant amplitude means the maximum displacement of the particle is called amplitude. Okay? And at a single frequency. That means the frequency of the vibration of the particle should not be changed. It always a fixed one. It is a single one. Then the oscillatory motion is called simple harmonic motion. Simple harmonic motion. So once again repeat, if the particle oscillates at or with a constant amplitude and at a single frequency, then the motion is called simple harmonic motion. Simple harmonic motion, right? If any particle executes a simple harmonic motion, the acceleration experienced by the particle is always directly proportional to displacement. Is always directly proportional to displacement. Or on the other hand, the restoring force experienced by the particle is also directly proportional to the displacement of the particle. Displacement of the particle, right? And this restoring force is always tries to bring back the particle to its mean position or equilibrium position, right? In simple harmonic motion, which point is, or which position is called the mean position? The position where the velocity of the particle is a maximum is called mean position or equilibrium position. The position where the velocity of the particle is zero is called extreme position. In simple harmonic motion, there are two extreme positions and only one mean position. Only one mean position, right? Generally, the simple harmonic motion is expressed in either sine function or cosine function. Sine function or cosine function. For example, if the displacement of the particle which executes simple harmonic motion is represented by y is equal to a sine omega t. Y is equal to a sine omega t, or otherwise y is equal to a cos omega t. A cos omega t. In simple harmonic motion, the displacement, acceleration and velocity of the particle can be expressed either in sine wave function or cosine wave function. So that is why this oscillatory motion is called simple harmonic motion. Simple harmonic motion. Right? From simple harmonic motion, some relations are there. That is a suffix x is equal to minus b into x. A suffix x acceleration experienced by the particle and x displacement of the particle and b is a proportionality constant. And another one relation, f suffix x is equal to minus k into x for one dimensional case. Here f suffix x restoring force, x displacement of the particle and k is a force constant or spring constant. Right? How can you measure the force constant or a spring constant? Okay, from force and displacement graph, the nature of the graph is a straight line. By taking a slope in that graph, from which we can calculate the spring constant or force constant, right? Okay students, so today enough. Please you go through all the topics. If you have any doubt, you call me. Okay, right? Thank you. We will see you in the next class.